Okay, brilliant. Over to you.
Okay, thank you for the introduction. And yeah, I'm Francesca Rossi from Scuola Superiore Meridionale in Naples, and I'm currently spending my period abroad for my PhD in Santa Barbara. And today I'm going to talk about my work on neural policy composition from free energy minimization that I developed in collaboration with Veronica Centorino, Francesco Bullo, and Giovanni Russo. And so this is a brief outline of what I'm going to talk about. And I will start by motivating the problem and clarifying what we mean by compositionality. Then I am going to introduce the normative framework that we define, explaining the details of how we formalize the composition as a free energy minimization problem and how we derive a continuous time dynamical system that can solve it, and how this dynamical system admits an implementation as a recurrent neural network. And then I will present some applications to collective behavior and human decision making where our model can provide some interesting insights on what happens. And then I will give some conclusions. So let me start with the motivation. What is compositionality? Compositionality refers to the ability to construct new complex behaviors by combining simpler primitive elements. And this ability is widely considered a hallmark of natural intelligence, and is emphasized both in neuroscience and artificial intelligence. In fact, humans are able to reuse and combine what they learned in order to perform new complex behaviors and fulfill new complex tasks. And in this work in particular, the basic elements are primitive policies, which we can represent as simple skills or behavioral strategies or mental schemas. And we focus on how they can be combined. And so we address some key open questions, which are: what is the principle that underlies the composition of primitive policies? And what is the gating rule that emerges from this principle? And can this mechanism be implemented in a neural circuit? Policy composition has been studied in many different fields, and in particular, it represents a transversal challenge across machine learning and neuroscience. And on the side of machine learning, for example, mixture of experts models combine multiple predictors through a gating mechanism. Hierarchical reinforcement learning organizes behaviors at multiple temporal and spatial scales. And Mosaic instead is a modular control architecture to combine multiple controllers. On the side of neuroscience instead, we have some different studies that evidence how neural circuits are able to flexible switch or gate between different cortical representations, including some thalamic and prefrontal gating mechanisms. However, despite all the advances, the existing approaches typically rely on some hard-coding switching rules or fixed combination weights or black box learned gating mechanisms. And so this makes them very tied to the specific architectures or tasks and datasets. What is missing and what is our objective is to define a general normative principle that explains how primitive policies should be combined in an optimal and interpretable way. So our problem comes in hand, and in particular, we define our model based on three components. First, we define an optimization problem, which encodes the task of the agent. And this optimization problem will be free energy based. Then we will implement an interpretable dynamics with the desirable properties that is able to solve this optimization problem. And lastly, we will implement this dynamical system as a neural circuit that is biologically plausible. So let me start with the definition of the normative framework, where by normative framework we mean that the composition uh, is performed by defining first the principle and explicit objective function behind it. And then once the objective is defined, the gating rule and the neural implementations are derived as natural consequences. And so let me start with how we encode the agent task. We consider an agent interacting with an environment, and specifically at time step k, the agent receives the state xk-1 from the environment, which represents the current information, and performs an action uk. The environment is assumed to be stochastic and Markovian. Therefore, at each time step, the state depends only on what happened at the previous time step. And the agent has this set of primitives, which are basically simple policies like basic skills or behaviors or mental schema, and that we call pi. Each primitive is a probability function that maps the current state to an action. And the agent also wants to perform a task by using these primitives. And in order to perform this task, he samples his action from a policy, PU. And what we are going to address is how we define this policy given the set of primitives. So we have this setup where the agent has this set of primitives. And these primitives enter a gating mechanism which outputs the optimal weights W star that we use to weight the primitives and linearly combine them to obtain this optimal policy. This gating mechanism naturally receives also the information about the environment, so the transition model, how the environment evolves, and a generative model, which in this case encodes the task of the agent. And how do we implement this gating mechanism? Specifically, we want to find the optimal weights that solve this optimization problem, where we minimize this free energy functional that is composed by two terms. The first term is a statistical complexity, which is a Kullback-Leibler divergence measuring the discrepancy between how the system behaves, which is the probability P, and the generative model, which encodes the task and is we call Q. Moreover, we add this entropy regularization term, which will be very useful because we will see that it will make the problem strongly convex and will allow us to have a unique solution and some very other interesting properties. The policy, as I said, is the linear convex combination of these primitives according to the weight that we want to find. So to better understand the framework, we can consider an example that we are going to recall later. And in particular, we consider the collective behavior of a flocking system. In this system, each bird that we also call the Boyd has as a state its current position and velocity. And this action is the acceleration that determines its motion. So we consider this second order system for the dynamics. And it's very well described in the literature as the Boyds typically tend to move according to three social forces, which are separation, alignment, and cohesion. So separation prevents collisions with the nearby agents. Alignment encourages to match velocities with neighbors, and cohesion attracts the agents toward each other so they don't get too far. So we define three primitives, which are three Gaussians centered in these three social forces. And the composed policy that the Boyd will use will be a convex sum of these social forces. The generative model instead will be, as we will see, depending on the neighbors, and according on how we define this generative model, we will reproduce different well-known behaviors in the literature of this kind of systems. So now we can formalize the policy composition problem. So given the environment model, the generative model, and the set of primitives, we want to find the optimal ways that minimize this problem, where in particular the weights have to be in the simplex, so they have to be non-negative and they have to sum up to 1. This is because the policy Pu has to be still a probability function. And the first term, as I anticipated, is this statistical complexity between P and Q, where P represents the interaction of the agent and the environment. So it is a probability in both in the state and the action, which can be rewritten as the product of the transition model Px and the policy Pu. And Q is our generative model, which encodes reference behavior, the task that the agent wants to perform. And then we have this entropy regularization term, where epsilon is a temperature parameter, which allows us to design how sharp we want the weight distribution to be. So the smaller epsilon, the sharpest the weight distribution will be. And this formulation is connected to the free energy principle. In fact, we can rewrite this objective function with an explicit cost by setting the generative model in this way, multiplying it by the exponential of the negative cost. And Z here is just a normalizer, and C is this explicit cost. In this case, substituting this definition, we obtain that the complexity term becomes like this. We have the Kullback-Leibler divergence plus the expectation of this explicit cost. And then we have this term that is just a scalar, so it doesn't depend on the weights and it can be dropped. And this is the free energy functional that appears in this paper, this recent paper, that is distributionally robust free energy principle for decision making. And it can also be related to some maximum diffusion optimization problems. And also here, what is interesting is that we have also this entropy term on the weights besides the free energy minimization. So our formulation allowed us to set this framework in which the agent is a probabilistic decision maker, which is related to the probabilistic brain theory, and to define a minimization of free energy plus entropy regularization problem that is strongly convex, so it has a unique solution. And it also allows us to harmonize the principles with the data-driven frameworks. And now what we ask is, what is the emergent gating rule that comes from this problem that we just defined? So we pass to the second part of our model, the dynamics. So given our minimization problem, where I just rewrote the Kullback-Leibler divergence as F for brevity, we have that this constraint problem, where the weights are in the simplex, can be rewritten as an unconstrained problem by defining this function H barrier, which is an entropy barrier, and is equal to minus entropy when the weights are in the simplex and to plus infinity otherwise. Then we apply a simple mathematical trick that is subtracting and summing a certain quantity. And this will allow us to translate the optimization problem into a dynamical system by using the proximal gradient of this quantity that I selected. In particular, the proximal gradient is a way to perform the gradient descent on some objectives that are that have a smooth term. That is, in this case, is the one that comes from the mismatch with the generative model, and then no smooth term that is, in this case, is related to the entropy. So the proximal operator is like taking a gradient step on the smooth part, and then a soft correction that enforces the constraint, in this case, the entropy regularization. And it turns out that in this case, this proximal gradient has an explicit form, which is the softmax. So we define this softmax gradient flow, and we know that the optimal solution of the minimization problem that we saw before is the equilibrium of this dynamical system. And it's very interesting because the softmax is usually is widely used for this kind of gating mechanism, but it is usually just arbitrarily assumed or heuristically. Instead, here it comes naturally from the definition of the optimization problem. And here we also define a timescale tau that allow us to module how fast this system converges. And as I anticipated before, here varying epsilon allows us to have more sparse or dense gating. When epsilon tends to 0, the gating will be more sparse. And otherwise, when epsilon increases, the weight distribution will be more uniform. So given this dynamical system where we saw that the softmax is the gating rule and F still encodes the agent task, we found some very interesting properties starting from the fact that this strongly contracting with respect to the Euclidean norm, which means given any initial condition that we have for the weights, it will always converge in a global exponential way to the unique equilibrium, which are the optimal weights that we want to find. Moreover, the simplex is forward invariant for this system, which means that the weights during their trajectory will always stay in the simplex, so in the feasible set. And it is naturally interpreted as a firing rate because it is non-negative and continuous and normalized. And it is also an energy model, as at every step, the cost function, which includes the statistical complexity and the entropy regularization, decreases monotonically. So the next question that we address is, can this computation be delivered by a neural circuit? And we pass so to the third element of our model. And in order to do so, we consider du discrete actions, and we define this matrix pi of primitives, which has on the columns the primitives values for all the different actions, conditioned on the current state. So we recall our dynamical system, and we can write explicitly the gradient inside the softmax. And we separate it into two terms, where the second term, which is related to the complexity and log likelihood, we consider it as an external input. And we can implement this mechanism as two units. In particular, the one inside the softmax related to the gradient is a fast unit. And the output of this fast unit is received by the softmax unit, which is slower. So this is the recurrent neural circuit that comes out from the from this dynamical system. And here we see that the circuit requires only summations and multiplicative modulations. So these operations are compatible with the classical models of dendritic computations, such as the sigma pi neuron introduced by Mel. And in particular, as I anticipated, the gradient that is inside the softmax is the first unit that is fastest, and it can be rewritten as this set of equations where each equations represents one of the operations in here. And obviously, these equations are separated on different timescales in order to have the correct computation. And then the output of this unit is passed to the softmax slow unit. The implementation of the softmax, for this we were inspired by this paper, Biological Softmax by Snow. And here we notice that the peculiarity is that M is a faster node which receives in input the sum of all the Y nodes. And it has to be faster because it is in charge of the normalization that is present in the softmax, which is non-trivial. So this is the complete set of equations, opportunity with the opportunity time scales. And we saw that this allowed us to define a soft recurrent neural circuit, which, given the current state, returns the optimal weight. And this system also benefits from the softmax flow properties that we saw before, and it is compatible with the dendritic computations. So just to remark what we saw until now, we defined our model based on these three components. And in particular, first we defined the optimization problem, minimizing free energy to find these optimal ways to perform the compositions. And the second part was the dynamical system related to this optimization problem. And we know that this dynamical system is strongly contracting, so it converges to the optimal solution of the problem. And then we define this recurrent neural network, which implements this dynamical system. Now we are going to see some interesting applications. And the first one, as I anticipated, is a collective behavior analysis. And in particular, we want to study how the composition of social forces generates different collective behaviors by simply modifying how we set the generative model. In this first case, we show how we can recover the polarization collective behavior, which is the collective movement where all the voids translate together with the same velocity. And in this case, we just set the generative model to encode cohesion and alignment with neighbors. And what is interesting, here we see the polarization metric, which goes to 1 when all the voids are polarized. And what is interesting also is that after an initial transient, these are the weights of one representative void. All the voids have more or less the same weights distribution. After an initial transient, they tend to be uniform in this configuration. So it's like they are using all the forces equally. In this second case, we just set some different initial conditions for the voids, and we also add an explicit cost in the generative model for the collision avoidance, and we measure the milling probability. Milling refers to the collective motions where all the voids circulate around the common center, forming a sort of vortex pattern. And here we also see the evolution of the weights for one representative void. And what is interesting is that just by setting these different initial conditions and this cost for the collision avoidance, we can recover this also well-known behavior. And the voids can keep this behavior just by evolving their weights. And here we see the separation weights tend to be a bit higher when necessary because of the collision avoidance cost that we added. In this last case, we reproduce the migration towards a goal. So in this case, only a few voids, in particular the 10%, have in the generative model have encoded this goal-directed movement. And so here we see the red agents are the ones that are informed about the goal, while all the other ones are just performing cohesion and alignment in the generative model, as we saw before for the polarization. And what is interesting is that these very few voids which are informed about the goal seem to guide all the other ones, that the other ones still stay polarized, but they kind of follow these informed agents toward the goal and start to rotate around it. And what emerges here that is also interesting is that the weights of the informed agents tend to be more flexible in the sense that they change more with respect to the uninformed ones that are just following. And this can also be related to what in the literature is found as the increased adaptability and flexibility of the leaders of a group. So we can consider the informed agents as leaders. Next, we address a big questions that is, how do humans balance exploration and exploitation? And in order to understand this, we analyze some real data from this paper, Deconstructing the Human Algorithms for Exploration by Gershman. And in the paper, two samples of participants performed two experiments of a two-armed bandit task. These tasks consist in trying to obtain the maximum reward by repeatedly choosing between two actions, each with an uncertain reward. So therefore, each participant has to try to balance exploiting actions that seem good with exploring actions to learn their value. And in the first experiment, one arm has a stochastic reward and the other one has a fixed reward to 0. And in the second experiment, instead, both arms have stochastic reward. In this case, for each participant, the state is composed by the mean and variance estimates of the reward per arm, which are obtained from a Kalman filter. And the action is simply to choose arm 1 or arm 2. In the paper, the author defines an hybrid policy in order to explain this data. And in particular, this policy is made of two components, which are the directed exploration and the random exploration. The directed exploration component tends to give a bonus for exploration, while the random exploration component tends to make the policy more randomized as the uncertainty increases. And these two components are weighted with the fitted parameters which are fixed and fitted on the data. What we want to do is to interpret this policy that Gershman defines in terms of simpler and interpretable primitives. So we define the generative model as this hybrid policy, and we define three simple primitives that in this case can represent mental schema. The first primitive is a greedy policy, so it tends to choose the arm with the highest mean reward estimated. The second primitive is uncertainty seeking, so it will tend to choose the arm which is more uncertain. And the third one is risk aversion, so it's kind of the opposite of the previous one, and it tends to choose the arm which is less uncertain. So by defining these three primitives, we found out that here we compute the peak speed, that stands for protected exceedance probability, and it's the probability that a given model is more frequent than the others in a certain population. So we found out that our approximation of the hybrid policy through these primitives achieves a higher peak speed than the hybrid policy itself, so it can better interpret the data. And it also allows us to have some more insights on the analyzed data. In fact, here we see the weights of the three primitives, and we see that in the first experiment, the highest weight is the one for the uncertainty-seeking primitive, which makes sense because I recall that in the first experiment, one arm is stochastic and the other one has a fixed reward to 0. So in this case, it's like humans tend to choose the arm that of which they don't know the outcome. So they tend to explore more to understand if they can obtain a better reward from it. And in the second experiment, instead, where both arms are stochastic, we see that the greedy and risk-averse policies primitives have higher weights. We also see that there is a sort of repetitive pattern in these weights, which can suggest that the humans in this in the same setting can tend to use the mental schema in a similar way. In order to understand also if our model is good for predicting, we perform this threefold cross-validation, which basically consists in dividing the dataset into three folds and using 2 of the 3 folds for fitting and the other one for testing. And then we compute the mean and variance by exchanging the folds. So here we evaluate the predictive performance by computing the predictive log likelihood, which measures how well a probabilistic model can predict new data. And the less negative it is, the better. And so also in this case, our model seems to capture the features of human behavior in a better way. So we have a less negative predictive log likelihood, which is better. I will give now some conclusions. And the key insights that we saw in this talk is that we introduced a normative framework for policy composition based on the free energy minimization. And this framework yields an emergent gating rule, which is the softmax, and which has strong dynamical guarantees. And it also means a biologically plausible neural implementation. And it can be applied across many different domains, which go from biology to neuroscience, robotics, and also others. Some limitations is that here we assume that the primitives are given, so they are already defined, but one could ask, what makes for a good set of primitives? How can we choose them? And some future work could also be embedding some learning for these primitives. And there are also interesting links with game theory, collective intelligence, and other frameworks that are very interesting. So I want to thank my collaborators, which are Giovanni Russo, Veronica Centorino, and Francesco Bullo. And thank you for the attention, and I'm happy to take any question.
Great. Thank you so much, Francesca. That was a really nice presentation.
Thank you.
Okay. Would anyone like to ask a question? Please just unmute yourself or raise a hand in the chat.
Hi, can I ask a question? Sorry,
Yeah, please.
Yes.
I couldn't find the raise hand button. Um, yeah, thanks so much for the chat for the presentation. It was really cool. I have a question about the collective intelligence or the collective
Yes.
behavior one you showed. That was really nice results on the informed versus uninformed individuals. I was wondering, have you tried doing it with multiple goals? So you have some individuals want to go to one goal and other individuals want to go to another goal.
Mm,
Yeah.
that's a very interesting idea, actually. We didn't try. Uh, what we tried was until now was to set, for example, different models, uh, different dynamical models for the informed and uninformed agents. So we try to implement the most famous models, for example, VSEC or Kagersmail, and it still worked. So the informed agents could still manage to guide all the flock to the goal, but we didn't try to set multiple goals. And I think it's an interesting idea that we could explore.
Yeah, cool. The reason I ask is because there's some very interesting work on how having multiple targets in these settings
Mm.
leads to like kind of there's some physical intuition or physical results on the symmetry breaking that results when you have that sort of setup. And like how
Mm.
the symmetry breaking is a function of the angle between the goals. And I wonder how that would relate to this softmax update rule for the weights. Because I expect already in the policy weight updates, you have this kind of nonlinear recurrent aspect that you get from the softmax. So I think that this model may be a good candidate for studying symmetry breaking at the collective level when they're kind of splitting into to track multiple targets. But yeah, thanks for the talk. It was really
Yeah,
interesting.
thank you. Also, if you have some references about this, I would be interested in receiving them.
For sure. Yeah,
And
I can
yeah,
send them to you.
thank you.
Thank you, Connor. Any more questions?
You tried to tune the number of informed agents over the uninformed agents to see what happens in this scenario?
Uh, Sorry, can you repeat the question? It was a bit.
Because, yeah, can you hear me?
Mm. Yes, okay.
Okay, have you tried to change the number of informed agents over the uninformed one to see what happens in this scenario?
Yes, we tried, and we tried with different numbers, proportions of informed and non-informed, and also with different number of total agents. And in general, we found out that until more or less the 10% of informed agents, they can always reach the goal altogether. But if we if the informed agents are less than 10%, they tend to split. So uh, it's more unlikely that they go all together to the goal. But until the if we have unless the 10%, they can always go all together.
Okay, thank you.
Yeah, also because the informed agents are kind of selfish, so they want to go to the goal, but they don't want to guide all the others. This thing emerges, and if they are not enough, they will just go selfishly to the goal.
But also, for example, if you have, for example, 95% of agents that are informed, you have a behavior like the one that you showed before. So in which they don't reach the target, they just rotate around the target position.
Yes, yes. If we have at least 10%, yes.
Okay, thank you.
Hi, Francesca.
Hi,
I do have a small question, if I may. So very nice presentation. Thanks a lot.
thank you.
Just about the circuits that you presented. You talked about fast units, slow units. So I was just wondering whether you have some ideas of how it could be implemented in the brain. So, for example, what part of the brain and what type of neural circuits? Like, have you thought about it, or is it just,
Yeah.
or did you stay at that level? Yeah.
Yeah, this is a very interesting question. Actually, yeah, we found some kind of references on how this could be a biologically plausible mechanism, as yeah, it is compatible with some mechanisms that exist in the literature, which are considered biologically plausible. And at the same time, we have this peculiarity that these synapses, which are the columns or rows of the matrix pi, are conditioned on the state. So it's like they are evolving according to the state, according to how the primitives evaluate the action conditioned on the current state, which is a peculiarity that yeah, it could be justified according to some literature, but we are actually it is a good point, and yeah, we would like to explore more on how this can be actually biologically implemented.
Okay, perfect. Thanks a lot.
Thank you.
I wondered if there's any sort of theoretical basis, even just for the original, I guess prior on having a linear sum, like a weighting mechanism in the first place. How do you I guess you treat this as a sort of prior assumption that you begin with some weighting mechanism, and then you find a free energy policy for that. Is there a way to motivate even beginning with a linear sum of policies from either from a biological or a free energy point of view, or is that something you take as the initial step?
You mean if we consider the mechanism as given, or
Yeah, it
yeah,
seems that that's the first stage to this. Yeah.
yeah, it's like this implementation is this is the natural implementation of the gating rule that we saw, and the gating rule that we saw naturally emerges from the free energy minimization problem. So yeah, the principle at the base is this free energy minimization problem, and then everything is naturally connected to it. It's not assumed or imposed. It's just the consequence.
And in the Boyd's model, are there any scenarios or initial conditions where you get sort of dynamically changing or more unpredictable behaviors rather than converging around a particular attractor or
You mean
so yeah, so in the second example you have this milling behavior.
Yes.
I suppose in the Boyd's model that corresponds to a particular set of initial conditions, but are there scenarios where where the weights don't fall into an attractor and you observe some more unpredictable formations? Or is it always the case that they end up with some predictable attractor state?
Yeah, it's like it really depends both on the initial conditions and on what we set in the generative model. In this simulation, we recovered milling because yeah, all of the Boyds had the same generative model, so they kind of tend to have this pattern. But I guess if we set up different generative models and, for example, some go to the target, we could obtain a different behavior, which yeah, is not so predictable. But yeah, it really depends on many factors. But what we found interesting is that just by changing the generative model of one or all the Boyds, we can recover these behaviors that are well known in the literature, and usually they are modeled, let's say, with the parameters that are properly fitted or with fixed weights that are properly fitted to reproduce them. Instead, here the weights emerge from the mechanism, and they allow us to obtain different patterns, different behaviors, just by changing the generative model without having to set them to do that.
Okay, any more questions from anyone?
If there's time, I could have another go. Yeah, it's interesting this just on this last exchange about the different regimes. So in the original model called the cousin model from 2002, it's almost identical except there's two zones, or actually there's variants with both two and three zones. But they find that there's certain parameter regimes where you have both milling very stable as well as polarization. But there's this other third regime called dynamic parallel group, where you have this multi-stable behavior where sometimes they're milling, sometimes they're polarized, and the polarization is never at 1. It's like more around 0.8, 0.9. So I would expect, because your model has a lot of those same properties, that there's probably some configuration where you could also get this dynamic parallel group. And then it would be interesting to know what the weight dynamics are in that case. I expect they would be oscillatory and kind of complex value, like, yeah, just have complex dynamics themselves. That's
If you're
not a
talking,
question, just a thought.
yeah, yeah, actually, we were inspired also for this application from the paper Collective Behavior from Surprise Minimization that is very related to this topic. So yeah, I guess there is a lot of analysis that can be made also according to what you're referring to, and it will be interesting to do that. Yes.
Yeah, definitely. In that paper, the the thresholds between like probability of milling versus polarization versus this more dynamic group was based on the precisions
Yes.
associated to the generative model. So in those little Gaussians you have over xt given xt minus 1, it's basically the precisions or the variances associated with those Gaussians were the key things that determined whether you're in one of these regimes. But it's interesting that you're getting that behavior, but you're getting it through the weights on the policies. Is that right? These W's?
Yes.
Yeah.
Yes. It's
Interesting.
the weights are changing and allowing us to obtain these different behaviors.
Mm, cool. Thanks.
Thank you.
Okay, any final questions? All right, if that's it for the moment, then thank you, Francesca. We'll hand over now to Carl for his feedback and summary of the talk.
Thank you.
Thank you. Is it my turn now?
Yeah, your turn, Carl. Over to you.
Excellent. That was a wonderful talk. Thank you very much. This is clearly, you've clearly done an enormous amount of work, and this is quite a mature program. And I'm glad that Connor is here. Connor, so when you had to leave from our previous meeting, you had to come here. Is that? I didn't realize that.
I was double booked for like 15 minutes with another person.
Oh,
That's
I
why I came
see.
late to this meeting. Yeah.
Yeah, I should apologize for arriving late. We had an emergency meeting immediately prior to this meeting. But I'm glad to see that Connor is here because um, a lot of his work touches on the themes addressed certainly by this sort of swarming behavior. Yeah, I repeat, this is very impressive work. And also to acknowledge it's quite mature. It's done a lot of stuff. And there are many ways in which I could sort of celebrate, congratulate, and look to links with other spheres such as control theory and other different kinds of active inference. Also, I got the impression that part of the agenda here is to link the implementation of this simulated behavior, and one could almost say application of control theory in this sort of very high-end context to neurobiology, both through the collective biological behavior of agents, but also choice behavior in humans, and how that could, these models of choice behavior in humans can actually now be modeled and parameterized, and applied in things like computational psychiatry. And then you have the questions and the focus on neurobiological plausibility and a neuromorphic implementation, speaking to the neural dynamics in terms of fast and slow. So there are lots of themes that I think should be acknowledged, and all very laudable. I'm going to focus in terms of feedback on what might be a useful forward direction of travel from a theoretical point of view. So I'll mention a few things which I think certainly have great potential, but my main focus is to a certain extent on touching upon the last exchange with Connor, which is, it would be really nice if the functional form of the implementation that you have used can be linked in a formal way to the formulations used in the free energy principle and its application to active inference. So basically joining the dots, because if you can join the dots, then you can sort of lend a lot more substance to the response. Oh, we just minimize free energy and therefore everything else is an emergent property. I think that's a great response, but you also need to explain why is it that or what particular aspects of the generative model produce the different kinds of emergent behaviors. And if you understand the mechanics of that, then you're now in a much more stronger position then to sort of deploy this technology in artifacts, say, drone research or autonomous vehicles or the like, or indeed as models of particular behaviors. Swing fish or choice behavior. So that's what I want to feedback. What I normally do is just sort of try to remind myself of all the key points that have been addressed during the presentation, by picking out a number of papers from the active inference space that you can, if you want to, then go back to and see, I repeat, the formal links between the implementation that you've engineered and what would be derived from first principles. I suspect that you probably know of most of the papers, but for other people and people watching this recording, I'm going to actually show Connor's paper, the collective, the surprise minimization that can explain collective behavior, because I think that is a very pertinent one, and speaks interestingly to that sort of discussion about the role of the W's, the gating roles, and what at first glance might be looked at as a kind of precision, in the sense that normally precisions do a weighting, but I don't think that's the right perspective here. If I was trying to sort of put this particular implementation of free energy minimization and implicitly active inference into a certain class, then if I understood it correctly, the gating weights, because they sum to one, can play the role of a probability. So in that sense, it's very much, in Bayesian statistics, this would be basically Bayesian model selection, or you could argue Bayesian model averaging, but if the one W is very big in relation to the rest, you're effectively modeling, I think, in exactly the right way. You're effectively modeling action or policy selection as Bayesian model selection, and therefore your W's now correspond to the probability of this primitive given my posterior over X and U over the latent states or the state estimators and the current control variables or policies U. And I think that resonates very much with sort of early formulations that you introduced at the beginning, like the mosaic from Kenji Doya and Walpert. It's not David, it's Daniel Walpert. And I think that but if it can be formulated like this, that you are doing action selection via Bayesian model selection, where you're very carefully picking out the most probable action given what the agent believes at the present time, I think that's a very compelling way to sell the story. And it also allows you to say, well, okay, if this W is so important in action selection and determines all the subsequent behaviors, what is a functional form, or what's the objective function that the W's are minimizing? And you would say, well, it's a form of free energy, and you decompose that in terms of relative entropies and or KL divergences and that embed a cost term or a utility function based in terms of the target distributions, and augmented with this regularizing entropy term. And what I'm hoping, and I don't know, but I think if you had a spare month, it would be nice to show that this had a formal homology. This will have the same functional form as the expected free energy that we use in active inference. And the functional forms do look similar to me, but they're not identical. So this is an open question, which I think it'd be really interesting to pursue. And I'll show you the sort of my favorite sources of the equations that you can then go back to and see, oh yes, that's just another way of writing down this equation, and then explain to people what the close connections are. And once you've done that, of course, you can then say, and we now have a very fast and efficient, neuronally plausible, neurodynamic kind of gradient descent that is beautifully regularized, and that one can imagine actually being implemented both in a recurrent neural network, but also in a neuronal network in the brain, which speaks to this sort of neuromimetic agenda that you're also committed to. But there's one slight twist in this, which is that the expected free energy is only appropriate for planning as inference. So it's appropriate for what in some circles would be called sequential policy optimization. And yet the problems that you have addressed, and certainly in the Boyd or the swarming simulations, these are sufficiently described by state action policies. So there's a fundamental difference between identifying the most likely policy, and if you're in control theory, the optimal policy, that is basically, what do I do given the state of the world S sub t is this, and optimizing the sequence of a set of policies which gives you a path into the future. So that moves you from state action to sequential policy optimization, where you now have to use a path integral of your free energy, and that's effectively the expected free energy. So I think it'd be important, just in the first instance, just to think about and explain in future communications the fundamental difference between control theoretic approaches that just try to optimize state action policies. So there's always the best thing to do, given I know what the state of the world is, as opposed to planning into the future with future goals and intentions, which now the problem now becomes finding the path from now to the desired endpoint. And that usually rests upon a path integral of a free energy functional, which is the expected free energy. Uh, um,
Mm.
in my world, that difference is described in terms of merely reflexive active inference, where you don't need to even mention expected free energy, and full active inference with expected free energy. And I suspect that what you've pursued here would be most easily mapped to the merely reflexive active inference, simply because you are trying to optimize.
Okay.
And in that instance, by merely reflexive, what people mean is that if I can predict the most likely thing that I'm going to do, I can simply use my reflexes or my um, servos or um, actuators to produce what I predicted I was going to do. So I'm reducing my action simply to minimizing prediction errors or variational free energy, both in terms of belief updating or state estimation, but also in terms of realizing actions that are the most likely or the least surprising. So everything can be optimized using free energy. To a certain extent, I think that's what you've done, but I also get a feeling you've gone slightly further. Because of the similarity between the objective function that you've used for your W's that you're doing your action selection with, and the functional form of the expected free energy. So I'm not absolutely sure whether you're doing what in my world would be merely reflexive active inference. In an engineering context, this would also be known as KL control or
Yeah, control. Yeah.
sensitive control, also known as path integral control, but for the wrong reasons. The use of the word path integral is usually reserved for sequential policy optimization into the future. So I can't give you an answer, but I can at least show you the equations that will allow you to be able to answer me if in several months' time I said, are you doing reflexive path integral control or are you doing full planning as inference sequential policy optimization, or are you doing both, or can you do both?
Yeah.
So if you will indulge me, I'll grab the screen and just
Sure.
give you the papers that have the equations that I would be very interested in you deconstructing and relating to the equations which you're using. Now, how do we do this? Bear with me for a second while it catches up. Screen. Share. Excellent. Right, I'm hoping that you can see my screen now. I'm going to start off with a bit of eye candy. So this is a simulation of a swarm using merely reflexive active inference. And this is not about agents of a biological sort. It's actually work in drone research where the goals have to change as a function of time. There's a particular reason I'm showing this. Well, one reason is I think it's quite pretty. So these are little drones, and they've all got to fly on a mission to go and inspect something. And then when they've done their inspection, they have to sort of change their shape and formation and then go back to base. The the maths is very similar to what you've been using and also what Connor has employed in his simulation of swarming fish. But the difference here is that the generative model is actually time dependent, and the generative model entails different cost functions. Remember your C's in the definition of Q bar. So Q bar, I imagine, is a target distribution. So the C's that underwrite the differences in the cost functions in the Q bar are now changing as a function of time, as as this little swarm moves. And I'm showing that sort of, let me just stop this if I can. I'm showing that just because, yeah, okay. That's every problem I've broken my never mind. I'm showing that just because the way that you started with compositionality, I thought you were going to start talking about motor chunking. I thought you were going to start talking about approaches to having overall plans that contextualize primitives, that contextualize primitives of primitives, that contextualize primitives of primitives. In fact, you didn't do that, but I put this paper up there in anticipation that you would at some point generalize this approach so that you can now have this kind of optimal control theoretic process embedded in a slow one, that itself is embedded in a slow one. And if you wanted to do that, then there are a number of ways in which you could consider doing it. One approach would be to retain your commitment to continuous state space models. Alternatively, you can now move at higher levels of specifying policies to discrete state representations. If you do that, then there is a recent literature on the use of the renormalization group to do the rescaling and composition at different scales that will allow you to nest primitives within nested primitives within nested primitives. The work that I'm most familiar with is, however, restricted to discrete state space models, Markov decision process models, where you still have the free energy and you still have your objective function, your free energy objective, the form of, well, the free energy function you use to optimize the W's, which is not quite a standard variation.
Yeah.
I'm going to call that the expected range. So you still have those functional forms, but now they are not applied in the context of sort of Kalman filtering or extended Kalman-Bucy filtering or the like, or KL control. They're now applied in the context of discrete belief updates, and then you can compose them hierarchically under the renormalization group. And this paper, I don't think you are because you didn't pursue this line, but it did occur to me that you might be interested in the discrete state space formulation of hierarchical composition and decomposition of inference and actions at some point. But probably a more interesting application is to mix them both together. And that's why I showed you that little demo at the beginning, because what was happening there was that the context, if you in the sense of you showing different emergent behaviors under different values for different precisions and parameters of your generative model, and possibly different target distributions Q bar. Now, if you can imagine having a slow process, a discrete process that's actually generating the parameters that produce those different emergent behaviors, you can now chain these different emergent behaviors in an optimal way. So you can now have a composition of not the primitive policies that you're currently selecting among, but the entire behaviors, the entire sort of, all going off, all following each other, all, exploring, whatever you want to do. You can now categorize each of these classes of behaviors in terms of the priors or the parameters, probably of the C that constitutes the Q bar, that produce that particular kind of behavior. And now you can prescribe sequences of behaviors very, very slowly. And that's exactly how that little demonstration worked previously. It just changed the fixed points or the equilibrium points through through the target distribution. So just producing a sequence of different kinds of swarming behavior. And that, to my mind, is a really good model for how we work. That we have a succession of fixed points that the scheme that you've used, including the one that demonstrated the Boyd behavior, specifies the endpoint or the target for fast dynamics, fast self-organization. And then when they reach or get near the target, then you change the target, and then you go over here, and then you go over here, and then you go over here. And to do that, though, you need to have this mixture of discrete state space modeling and continuous state space control theory dynamics of the kind that you've now optimized. And this paper just takes you through the common maths of the two and then applies it to eye movements. Where's the picture? It applies it to eye movements so that you can simulate now very fast and very efficient epistemic or searching movements with very fast ocular motor dynamics using KL control. But you're now prescribing the targets of those sequentially in a lawful way to now model eye movements, for example, during reading, that we sort of jump to this word, and then we jump to that word, and we jump to this word, and jump to that word, which would be another kind of composition, not of the primitives, I repeat, but the paths or the dynamics that is engendered by selecting the right primitives during a period of time. Then you change the target distribution, and then you have this separation, even greater separation of temporal timescales. So that struck me as one potential way of extending this program, which is to put a discrete Markov decision process or hidden Markov model on top of what you've got already to prescribe composed sequences of behavior. Very much in the spirit of the sort of, I think, the mosaic approach. And I repeat, sort of from a maths point of view, it's really interesting because the underlying gradient descents, the dynamics that you focus so much on, has a very similar functional form, whether you're working in continuous or discrete state spaces, because they inherit from the same math, which is just, as you know, minimizing a free energy functional. In the sort of discrete high-level planning part, that would be an expected free energy. But just to, so for the record, this is the collective behavior from surprise minimization by Connor.
Yeah.
So just going through the equations and just mapping, that's a precision, that's a posterior probability. I think that will be really interesting, because in principle, at least with a part of the both of your implementations, they should be the same. If they're both doing a gradient flow on a variational free energy, then ultimately they should be you should be able to interpret one in terms of the other, and the only differences will be the particular specification of the underlying generative model. So there should be an answer there. It's just a question of whether that can be unearthed. But just the reason that I have the question in my mind is your free energy functional that's underwriting the action selection in the spirit of Bayesian model selection, basically elaborating a posterior over the primitives, given the current beliefs about the state of the world. Can that be related to expected free energy? And there are good reasons why you might want to do that. And just looking at what the functional form you're using, I would say yes. So this is this is one of many descriptions here, but very clearly demonstrates this decomposition into a KL divergence, specifically over random variables representing the state of the world and the actions. It's not actually actions. Let's pretend it's actions here. No, it's not actions. It's conditioned upon a particular policy. So you can look at this basically as a specification of log minus log W, minus log of the probability of W, such that when you apply your softmax function, it then becomes you then bring your W's onto the simplex, and they sum to one, and they can then be treated as posterior probabilities or weights for the primitives. So if you take your the fast arguments of the softmax function, this is basically what the expected free energy does. So the softmax of G will give you a probability over the policy pi. And that's why, and in that spirit, then this becomes, if you like, the objective function that is being minimized by your fast dynamics that are computing the fixed point of W for any particular moment in the simulation. And it has a very similar form to what you described, in the sense that here the target distribution is a P and the posterior is a Q, so it's the opposite way around to you.
Yeah, inverted, yeah.
Yeah, but if you just remember we switched the notation. But this stands in for Q bar and rests upon C, in the sense that it is the preferred state probability density, the target, if you like, over that is prescribed by some cost functional of either the outcomes or the latent states. And this is your posterior, or your approximated posterior that you've got from minimizing your variational free energy. So that's almost identical to your risk term. But there's also an ambiguity term, which is not the same as your entropy term, but it's quite close. It's in the sense that it's an expected entropy pertaining to the the ambiguity, or the the entropy of, or conditional entropy of, observations given the current states. So it doesn't play the same role of regularization. But it can also be interpreted as an entropy term, should you want to point to the formal similarities, even if they're not identical. I think it's an interesting observation. This basically licenses the notion of risk-sensitive control, where you're trying to minimize the KL between the most likely policy after when you apply your softmax operator, is that which minimizes the risk expressed as a KL divergence between your anticipated states given a particular action, or sequence of actions in this instance, but for you, you're only worrying about one action, even if you've actually got the mathematical machinery to do sequential policy optimization, there's no reason why you can't do this. You can now go one or two steps into the forward in time, because you've got your generative model of the dynamics. So now, instead of just optimizing the primitive at this point in time, you can now optimize, you can now create W, which is a posterior over sequences of primitives, and then take the marginal over the next primitive, and then that will be your W. So my suspicion is you can extend what you've got just by rolling out a few steps into the future, because you've got everything you need there. You've got the right generative model, you've got the consequences of any control variable on the state transitions. So now you can condition, if I pursue this action, I know how these states will evolve. If I know how these states will evolve, I can then compare them to what I want in the future. I can now evaluate the risk and the ambiguity or regularization term, and then I can take the softmax operator of that. So my suspicion or hope is that you have actually done sequential policy optimization. You just haven't actually done the next step. You've just used the
only
to
at the single step. Yeah.
So this is one of many papers describing active inference, but it's a particularly clear paper. But it does deal with discrete state spaces, so you're going to have to do your own mental gymnastics to work out the equivalent in continuous state space models, where the KL divergences now usually rest upon the Laplace the Gaussian form for your probability distributions. So it should be relatively simple, not as simple as discrete state spaces where these are just subproduct operators, but it should still be quite simple here. So that's that equation. Your multi-arm bandits thing. Again, it's interesting that you chose that as a sort of validation approach, and also it's interesting that you chose it to answer the question, not what is the optimal way to choose my multi-arm bandit, or to explore and exploit, but what's the best description of human choice behavior under the assumption that they use some Bayes optimal scheme. And that sort of, I think that's an important observation. I don't know whether you know about this, but in computational psychiatry, this is quite a big thing. This is basically you bring not an ideal Bayesian observer model to the table, but an ideal Bayesian actor model. So now you're in the world of active inference and control theory. You can now bring Bayes optimality not just to the Bayesian filtering and state estimation, but also in the spirit of optimal Bayesian decision theory to the choices that people make. So now you've got ideal Bayesian actor or decision makers under uncertainty. Now you've got a model of him, and of course that model is parameterized with particular priors and targets and precisions over those target distributions, their goals. And now, because you've got a formal model, you can, exactly as you did with your exceedance probabilities, you can now fiddle with the parameters of the generative model that produces the Bayes optimal decisions to match that of the human subjects. And that's what's called computational phenotyping in computational psychiatry. It's basically describing a person or a cohort of people in terms of their prior convictions and commitments and beliefs, but very formally under a well-specified generative model. So I thought that was a really interesting example. And the multi-armed bandit one, if you can solve that, then you can cast nearly every kind of paradigm or choice behavior or game theory paradigm under a multi-armed bandit sort of formalism. So I think that's absolutely the right thing to do. And this is an example of pitching, I can't remember, Thompson sampling, I think, or some related thing against expected free energy, very similar to the functional form that you've used. And if you ignore that difference between the ambiguity and the entropy, then I think they will be formally identical. And you can ignore that when you've got very, very precise observations. So when there is no ambiguity about the latent states, given my sensors, then your functional form and the expected free energy become the same. And at that point, you revert to KL control or risk-sensitive control in its sort of control theoretic or economics and control theoretic approach. So yeah, that was that. I don't think that's going to be very, you know all that already, but one thing which you might not know is that the expected free energy does not come from just common sense and trying to dissolve the exploit dilemma or trying to comply with standard optimal control constraints. You can derive the expected free energy, the functional form, from first principles, from the physics of random dynamical systems universally. And this paper sort of takes you through the derivations, and interestingly, the functional form. So the Lagrangian of autonomous paths of conservative particles. By conservative here, we're talking about particles that have fairly precise motion, like your swarm boids. So we're not talking about sort of small particles or quantum level particles that have very random or stochastic aspects to them. We're talking about agents that pursue paths of least action. And if the agents pursue the paths of least action, where the action now is a path integral of the expected free energy, of the free energy, then the Lagrangian of autonomous paths can be expressed as a free energy functional that entails optimal Bayesian design, that's the exploration, and decision making, that's your exploitation. And just note, now this again is the thing that you put into your softmax function to get your W's. It has exactly this risk term where now the Q is, or your target distribution is just P of the states that this kind of system goes to. And your P is now conditioned upon the particular policies with this ambiguity term. But interesting, this ambiguity term under this conservative assumption goes to zero. So the expected free energy and your free energy functional become identical, which is an interesting point, because what it means is that your objective function, it has to be universally true and demonstrably true from first principles of random dynamical systems, from the physics of non-equilibrium steady states. So if you're asked, can you derive it from first principles, your answer is yes. And then you go to equation 10 of this paper, which uses path integrals in this sort of more generic sense, as opposed to, although actually on reflection, they probably are the same thing, path integral control theory. So I thought that might be entertaining for you to get, where do these objective functions come from? They just come from the solutions, density dynamic solutions to non-equilibrium steady states, which when expressed in terms of paths, what you're talking about is the optimization of kinetics and dynamics and movements or choices in a more Bayesian decision theoretic context. Stop share. There we are. Good. That's all I had to say. Thank you.
Thank you so much for the very interesting ideas and possible extensions. I will look forward to that. And for the references, thank you.
Thank you.
Great. Thank you, Carl. And thank you again, Francesca, for a fantastic talk.
Thank you.
Okay. All the best, everyone. Thanks for joining today, and see you next time.
Thank you very much.
Thank you.
Thank you.
Thank you.
Thank you.
Bye.
Bye-bye.
Thank you.